me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students and just ask you to bless our work today, Lord. In your name I pray. Amen. So, today I'm misbehaving a little bit, but for a good cause. So just to review, what have we done so far? Up to this point, we've studied, we studied vector fields, right? And we saw, what do we see about vector fields? We saw that if we could find f of r of t equals to dr dt, right? If you could find the path which solved that equation, that would mean that the path has a tangent field which lines up with the vector field. And such a path is said to be a parameterization of the integral curve for the vector field. And I actually showed you for vector fields in the plane, this amounts to solving dy dx equals to q over p, remember? Or you could look at it as a system of autonomous differential equations. That we did that day one, right? And then last week, the next day, we looked at conservative vector fields, right? That's what we did Thursday. And we discussed how conservative vector fields, in other words, if f is equal to, say, pq, right? If that's equal to the gradient of some little f, then, well, then df is p dx plus q dy, right? And we said that if we have a differential equation which has the Pfaffian form p dx plus q dy equals to 0, what's the solution? Right, if we have this equation, then solution is f of x comma y equals to a constant, right? That's the implicit solution for an exact equation. That was a quick summary of what we did last time. But I mentioned last time that not every differential equation is exact, right? So the test for exactness we derived from, I think it was Green's theorem. What was it? So the test for exactness of m dx plus n dy, right? If this is exact, if what? We need partial m partial y equal to partial n partial x. Or if you use the PQ notation, what's the condition? What did I call this condition? So I mentioned if you took the curl of the vector field PQ0, then what you'd get is something, something, and then the interesting part, let's see over here, we get partial q partial x minus partial p partial y, right? It's the z component to the curl, actually. If p and q are both functions of x, then the first two components are 0 as well. But I called this condition I just wrote down, partial p partial y equal to partial q partial x, the closed condition, right? So I want to expand on that thought today and talk a little bit about what are called differential forms, which is a more modern way of doing calculus. If you study fluid mechanics and maybe some graduate engineering, you might run into these things. All right. But for us, if nothing else, they're just some fun math. So let's get to it. It's going to take me a little bit to get back to this idea of the closed condition as it meaningfully connects with the concept of differential forms. So we'll get there. To start with, though, I need to take a few minutes to talk about the algebra of the wedge product. So what's the wedge product? Well, so here's the basic ingredients. We have f as a function, and I'm going to do it. I'm going to do the wedge product for R3 because that's perhaps the most familiar to you guys. We have a function of x, y, z. A one form, alpha, is something like a dx plus b dy plus c dz. A two form, beta, is something like a dy wedge dy wedge dz plus b dz wedge dx plus c dx wedge dy. This would be a 2 form. So 0 form, 1 form, 2 form, a 3 form, also known as a volume form, gamma, something like g, dx wedge dy wedge dz. Now these wedges, you should just think of them as labels, formal constructions, if you will. I mean, what is dx wedge dy? It doesn't really matter to you. It just, you should understand that there is something called dx wedge dy, and it's different than dx. It's different than dy. It's some new thing. All right. I can give you a concrete mathematical definition, but after that was said and done, it really wouldn't add much to the discussion here. So let's just assume that there is such a thing and go forward with it. All right. Now, more than this, though, as I just wrote them, there's a natural correspondence with vector fields. All right, so 1 forms correspond to vector fields. How do they do it? What's the vector field that corresponds to that form alpha right there? It is the so-called work form. And so the work form, which I use omega for, omega sub a comma b comma c. So this is the 1 form corresponding to the vector field ABC. And this one, it's the flux form, capital Phi, of ABC. So the flux form of ABC is this. The work form of ABC is that. Now let me show you how we actually do the algebra. The key idea is that dx wedge dy is equal to minus dy wedge dx. So the wedge product for 1 forms, for differentials, it anti-commutes like that. And also, part of the same vein is any wedge product of a thing in itself, a 1 form in itself, is 0. So likewise, like dx dy wedge dy is 0, dz wedge dz is 0. So as a sample calculation, let's look at an example. Well, I guess I should do it here. Example. If we take the work form of the vector field 1, 0, 1, and we take the wedge product of that with the work form of the vector field, and I'll just keep it simple, 0, 1, 1, what do we get? Well, let me make these numbers 2 and 3 so you can see a little bit better. What is that? So this would be dx plus dz wedged with 2 dy plus 3 dz. All right, so we work that out. What do we got? We have 2 dx wedge dy plus 3 dx wedge dz plus 2 dz wedge dy, just distributing things through. That's another thing. Wedge products, you know, they got this anti-commuting, and much like the cross product, the thing with itself goes to 0, but otherwise they behave kind of normal. They have the usual distribution properties and so forth. All right. Now, I want to make it in the flux form pattern, right? So I need to like make things go dy dz, right? So I'm going to have minus 2 dy wedge dz. Next, I need dz wedge dx. So I got to flip that around, minus 3 dz wedge dx. And then finally, plus 2 dx wedge dy, right? So if you tilt your head and squint, you ought to be able to see that what we just found is the flux form of the vector, the flux form of the vector minus 2, minus 3, 2. Okay. So if you'll allow me to do some name calling here, if I call this vector A, and if I call this vector B, and if I call this vector over here C, what's the pattern? What's C equal to? Can you tell me how C relates to A and B? how about if I did this determinant of, I, j, k, for those of you who use that notation. Not me so much, but what's this work out to? I seem to have, oh, there's no minus. There's just one minus there, yeah. Right. So what is C? I mean, C is the cross product of A and B, right? It's the cross product of A and B. So this example is not an accident. In fact, it's the tip of a theorem, if you like. I mean, there's a theorem. What's the theorem? The theorem is that omega A wedge omega B is the flux form of A cross B. So in this sense, the wedge product is a way to implement the cross product in kind of a sneaky way. But this viewpoint of differential forms, it's more nuanced than the one you've been taught in Calculus 3 because it makes a distinction between two different kinds of vector fields. There's the vector fields which correspond to one forms, and there's the vector fields which correspond to two forms. In Calculus 3, those two kinds of vector fields, they're all muddled together. We don't distinguish them. But if you study advanced engineering and so forth, you might call the one kind of vector field an axial vector field and the other one's a polar vector field. If you study their coordinate change properties, they behave differently under inversion. And so there's a distinction between those kinds of vector fields, which I think is lost in the usual presentation. Because we just talk about vector fields, right? And you don't say, well, that vector field's like one of these one form kind of ones, and this is one of these two form kind. We don't even have one forms and two forms to talk about, right? So this distinction I'm making is not one we even address in our typical Calculus 3. But anyway, the wedge product can do the cross product like this. What happens if we take omega A, wedge omega B, wedge omega C? You know what that does? This ends up being A dot B cross C. So, and then over here you got your dx wedge dy wedge dz. So the wedge product of three things picks up the triple product, which of course is significant in that it gives you the sign volume of the three-dimensional cube, well, rectangular solid with side vectors ABC, right? Plus or minus, depending on whether those vectors are arranged left-handed or right-handed. All right, anyway, so there you go. This is the wedge product. It reproduces the dot product and the cross product that you know and love in this sense. And the interesting new features of the wedge product is that it behaves more or less like the usual algebra. One big difference, the wedge product is associative. All right, so like this thing I just wrote makes sense because whether you do wedge A and B first or wedge the B and C first, it doesn't matter, same outcome. In great contrast, the cross product is not associative. Like if some book tells you A cross B cross C like this, you can rest assured that whoever wrote that book doesn't really care about details because that is ambiguous. There is a difference, generally speaking, between this and that. Right? Those are different. The cross product is not associative. If you want to know how non-associative it is, you could write this: A cross B cross C plus A cross B cross C plus A cross B cross C. And let's see here. Aw, man. Just a second. I got to do some permuting. So I go ABC, I go CAB, I go BCA. So I just like that, you know? So if you add these three things together, you get 0. This is known as the Jacobi identity. All right. So the cross product does satisfy that. I mean, it's not, yeah, it's non-associative, but it's non-associative in that way. Great. Now the wedge product does not suffer these problems It's just associative. And you can calculate wedge products, and you can keep calculating wedge products all day long, and they're always associative, and it's pretty simple once you get used to these basic rules that you get minuses, and when you wedge product one form with itself, it's 0. So also, if you really appreciate that dx wedge dx is 0, you understand that there's nothing past this. You can't write a 4 form in 3 dimensions, because if you did, it would have 4 differentials wedged together. But how many coordinates are there in 3 dimensions? You got your x coordinate, your y coordinate, your z coordinate, right? You can't have a 4 form because you need a 4th coordinate, which is not available in all R3 independently, right? So there's that. That's the algebra in a nutshell. Let's move on to calculus. What's the calculus of differential forms? I'll try to be brief because I do want to get back to differential equations as soon as possible. But I'm going to make a meaningful connection with differential equations, what I'm doing here. So it's not just me talking about differential forms because I love to, although that is true. You caught me. It's okay. Is this in the syllabus? No, it's not. Is that okay? Are we allowed to actually talk about things that are interesting to one another? No? Out! Out! Ah. She's not saying that out of genuineness. She's just saying that to aggravate me, and I appreciate that. So, okay, so long story short, if we have a function, then we've already defined df. What was df? Df is, you know it, you love it, it's the, and I'm being 3-dimensional here. Of course, this would just have the first 2 things I already wrote if we're in 2 dimensions, and that should be a z. All right, so partial f partial x dx plus partial f partial y dy plus partial f partial z dz. This is the total differential. We already taught you this in Calculus 3. This is standard material, and it's also an entry-level calculation for the calculus of differential forms. This is the first thing. Everybody knows about this. So there you go. Now, what you didn't know, maybe, is that this is the work form of the gradient vector field. The gradient vector field is partial f partial x, comma partial f partial y, partial f partial z, and that is the work form of the gradient field. So that's kind of neat. There's more. If we have omega is a dx plus b dy plus c dz, now here, a, b, and c, these are all functions of x, y, z, generally speaking. And so, definition, the exterior derivative, or if you like, the derivative of omega, is simply the total differential of a, wedge dx, plus the total differential of b, wedge dy, plus the total differential of c, wedge dz. As engineers, I think the calculational program here is pretty clear, right? You just take d of stuff and add wedges as appropriate to make it make sense. I mean, that's a fairly easy heuristic to follow. And then the thing is, this dA, right, is what? It's like partial x a dx plus partial y a dz, dy, dz, listen to me, plus partial z a dz. That's my total differential of a, wedge dx. All right? And then similar thing, wedge dy. Similar thing, wedge dz. I don't want to write out the other two. I'm just going to focus on the a component. If I write everything out here, it takes me 5 minutes. I only want to spend half of it this blathering about nothing. So what happens with the dx wedge dx? Well, that's 0, right? And so if you look at this, this is going to give you partial a, partial y, dy wedge dx, plus partial a, partial z, dz wedge dx. And then from the b term, we get partial b, partial x, dx wedge dy, plus partial b, partial z, dz wedge dy, plus partial c partial x dx wedge dz plus partial c partial y dy wedge dz. Because 3 of the terms are 0, because dx wedge dx is 0, dy wedge dy is 0, and dz wedge dz is 0. So you put this together, what you got? For my dz, for my dy wedge dz terms, we've got partial c partial y minus partial b partial z dy wedge dz plus my zx terms, partial a partial z minus partial c partial x dy wedge dz. I'm sorry, I mean dz wedge dx is what I wanted there. And then, of course, partial b partial x minus partial a partial y dx wedge dy. Do you know anything like this from Calculus 3? Do you remember we take a vector field, we calculate partial derivatives of the components, we take differences of those partial derivatives and arrange them in a vector? What was that? It's the very end of the course. You all forgot it. I talked about it last class, though. We needed it for Stokes' theorem. Remember that? Stokes' theorem is stated in terms of the curl. These are the curl. These are the components of the curl of the vector field. The x component, the y component, the z component. In fact, this is nothing more than the flux form of the curl of the vector field ABC. So the exterior derivative of the work form is the flux form of the curl of that vector field. The same concept of differentiation that gives you the gradient gives you the curl. And more than this, though. If we take a flux form, right, a dy wedge dz plus b dz wedge dx plus c dx wedge dy, and I won't do the calculation, but it's not that hard to do. If you take the differential of phi, guess what you get? You get the divergence of the vector field ABC times dx wedge dy wedge dz. That's the 3-form derivative of the flux form. So the exterior derivative reproduces gradient, curl, and divergence from one unified program of calculation. So that's the differential calculus. You could say more, like there's a product rule and all kinds of neat stuff. But I'll stop there. I mean, I'm not trying to teach you everything about this. Integral calculus. So first of all, if you have a curve, C, that goes from, then you can talk about the integral along a curve of the work form of a vector field. Guess what that's defined to be? And if you've got a surface, you can talk about the integral over the surface of a flux form. I'll say of a vector field G. How's that defined? And if you got a volume, we call it E, the integral over that volume of the G dx wedge dy wedge dz, that's also an integration that we can. So what I'm trying to tell you is the way differential forms are integrated, it's actually kind of neat. If we're talking about a P form, a differential P form is integrated over a p-dimensional space. So 1 forms have to be integrated along curves, 2 forms have to be integrated over surfaces, 3 forms have to be integrated over volumes, and this story goes on if you had higher dimensional data. A 4 form would have to be integrated over a 4-dimensional subspace of your space. And all of these spaces I'm talking about are oriented. It's an oriented curve, an oriented surface, an oriented volume. And the definition is stuff you already know. Like this is just straight up the line integral that we talked about. This is the surface integral as usual. And the volume integral, you just drop the wedges. So the difference between, this is a formal definition, a formal integration that you've never seen before, unless you're in my Calculus 3, in which case this is a rerun for you, sorry. But you probably were checking out because you knew I wasn't going to test on it in Calc 3, right? Yeah. There's a good likelihood I'm going to ask a quiz question about this stuff, just, because that's a quiz question, and I'll find something to ask that'll be interesting. Anyway, so line integral, surface integral, volume integral, all of these integrations are present with the integral calculus of differential forms, and that's how you do it. So something beautiful occurs in this discussion, which is that there's a theorem which unites the fundamental theorem of calculus and Green's theorem and the Stokes theorem and the divergence theorem all into one unified theorem, which is known as the Generalized Stokes theorem. Generalized Stokes theorem states the following. Let's try it again. The Generalized Stokes theorem says the following. It says that the integral, the integral of a form, let's say alpha, over the boundary of some manifold is equal to the integral of the differential form d alpha. I mean the exterior derivative of the form d alpha over the manifold. Now I said manifold, but let's think about space. So the integral of a form over the space, well, rather the integral of the derivative of the form over the space is equal to the derivative of the form on the boundary. This is the Generalized Stokes theorem. What's this look like? So if we're integrating a function over the boundary of a curve, that will be equal to the integral over the curve of the derivative of the function. Now, this requires some interpretation, but if we're integrating, what's the boundary of a curve? If this is P and Q, what's the boundary? Or let's say P1 and P2. Yeah. So the boundary is just the endpoints, right? So here's the definition of this. What this means is f of P1, or P2, minus f of P1. And what's this? Well, this is equal to the integral of the gradient of f dot dr. So there you go. Generalized Stokes theorem applied in this context is just the fundamental theorem of calculus for line integrals. What is the Generalized Stokes theorem? If we do it here, we could look at, for example, we could look at the integral over the surface of, what's a 2 form? That's a derivative. Excuse me. How about d omega, right? So the integral of d omega over s is equal to the integral of omega over the boundary of s. What's that translate into? That translates into the integral of the curl. Oh, I'm sorry. I'm missing my sub f. The flux form of f. Excuse me, the work form of f. So this gives me the integral of the curl over the surface is equal to the integral of the vector field around the boundary of the surface. Sorry, I've worked myself into a my lecture's colliding with itself. My apologies. And then if you well, let's see, what's the other case we could look at? If we look at the integral over a volume of the exterior derivative of the flux form of G, that's equal to the integral over the boundary of the volume of the flux form of G, allegedly, right? Now that translates into the integral over E of the divergence of G, dx wedge, dx dy dz, right, is equal to the integral of G dot ds over the surface of the boundary V. And maybe you recognize this, that's the divergence theorem. Remember the divergence theorem says you can integrate the divergence over the volume to find the flux of the vector field through the edge. So Stokes theorem, the divergence theorem, the fundamental theorem of calculus for line integrals, these are all just special cases of the generalized Stokes theorem. And the generalized Stokes theorem doesn't stop at three-dimensional geometry. This goes on. This is something about the calculus of n-dimensional spaces. See, the curl that you've been taught in Calculus 3 is special to 3 dimensions. We can't talk about a curl in 4 dimensions, right? If you give me 2 vectors in 4 dimensions, can you give me a unique third direction from those 2, which is orthogonal to the given 2? You can't, because in 4 dimensions, there's 2 orthogonal directions to a given pair. So there's not a unique choice of that third vector. At best, if you gave me 3 vectors, independent vectors in 4 dimensions, that could be used to define like a tertiary cross product. Give me 3 things. I give you a 4th orthogonal thing. That you could do in 4 dimensions, right? So the cross product you know and love, or at least know, from Calculus 3 is no longer available in higher dimensions. So if you want to do calculus in higher dimensions, you're forced to do something different. And that something different is differential forms. So if you were such a person as to go study theoretical physics, you'd find that modern physicists are writing equations, not in terms of vector fields, but in terms of forms. So for example, the equations that govern string theory, a lot of them are written in terms of flux forms. Like the magnetic field is not a vector field, it's some kind of differential form. But now, not getting so esoteric, if you just study fluid mechanics, differential forms is a good way to write equations on spaces that are curved. So this calculus is just useful for curved spaces as well. All right, enough about that. So the theorem that I have hidden from you so far, which has more to do with differential equations, is the following. Theorem. The exterior derivative of the exterior derivative of a form is 0. So aka d squared equals to 0. So if you twice exterior differentiate something, it gives you back 0. So that's kind of interesting. And that essentially, well, I'm not going to prove it. It's true, okay? If you look at the details of this, that is a quick way of writing a couple of identities you saw in Calculus 3. Maybe you remember the curl of the gradient is 0, and the divergence of a curl is 0. Both of those identities are folded into this single identity, and a host of other ones we don't have names for. All right, but more. Definition. Gamma is exact if there exists, let's say beta, such that gamma equals to d beta. So gamma would be like a p form. What would beta be? It would be a p minus 1 form, right? If I'm taking the exterior derivative of a p minus 1 form to get a p form, I need 1 less degree, because when I take the exterior derivative, I raise the form degree by 1. The way I think of this is as follows. Basically, like the beta is a potential energy form, right? The beta is in some sense like a potential energy form for gamma. So this is serving in some sense of the role. It's like a potential energy for beta, for gamma rather. Can you find a potential energy function for gamma? I mean, the potential energy function is something you differentiate and get back to vector field. Maybe I should put a minus in to be true to the issue we talked about last week, right? So that's that. Another definition. Gamma is closed if d gamma is equal to 0. So a form is said to be closed if its exterior derivative is 0. Before I forget, this has got fine print. What's the fine print? It's exact on you. Ooh, I need to spell on you. So exact on a set. Just like we talked about conservative vector fields are conservative on some set, in the same sense, we're talking about exact with respect to some collection of points. There's a domain that's this is again happening for some subset of the space we're talking about. All right. So can you tell me given what I just wrote on the board, can you tell me anything about exact and closed forms? Let me ask you a question. If gamma is exact, does this imply gamma is closed? And why is that? Very good. So d gamma is d of d beta, which we just were saying is 0 because d squared is 0. Right? So right, exact implies closed. This is not up for grabs. That's just a consequence of this d squared identity, which, for what it's worth, rests on the symmetry of partial differentiation and the anti-symmetry of the wedge product. But let me focus here. How about the other direction, though? What about the other way around? If gamma is exact, then does it follow? Oh, I'm just writing the same thing down again. That's not a good sign. Not a good sign. If gamma is closed, right? If it's closed, does this imply that gamma is exact? Is this an if and only if? Or is it just one direction? Sorry to bring one direction into it. It happens sometimes. Did that make you throw up in your mouth a little bit? Or a little bit? Okay, that's good. Sorry, it's before lunch. I should, keep my unappetizing comments to a minimum. You're like, it's too late. You have a board full of unnecessary math. The day is already ruined for me. All right, let me go on. All right, so the answer is subtle. The answer is sometimes. All right, sometimes. In fact, there's something called the Poincaré's lemma, which, for the purpose of our conversation right now, I'll say this way. If U is simply connected, or you could say star-shaped if you prefer to. Maybe star-shaped is better because I can actually give a better definition for that. What does it mean for a space to be star-shaped? Here, I'm not doing well here. I think this space is star-shaped. So here's what star-shaped means, guys. You can pick a star center, all right? And from that star center, you can reach any other point in a star-shaped space by a line segment, which doesn't leave the space. Is that the case for my awkwardly written star? I don't know. Maybe. I think we can reach all points up to the limits of my artistry. Hopefully I haven't accidentally. I was trying to actually draw a star-shaped star. I don't always succeed in this. If you draw it too lumpy, part of the one of the arms of the starfish, so to speak, will be inaccessible. But yeah, this star is actually star-shaped. And so a space that's star-shaped is going to be simply connected. And you got to think about this three-dimensionally. Like you could think about a three-dimensional star, right? Like you put on your Christmas tree, perhaps, right? Okay, anyway, star-shaped would imply simply connected. Simply connected is a little bit more esoteric than that. But all right, anyway, so if U is simply connected, then gamma closed on U implies gamma exact on U, which means that there exists beta such that what? Gamma is equal to d beta. So Poincaré's lemma is the generalization of that exactness condition that I shared with you guys last class, right? Which was what? What was our theorem last class? I wrote it over there. Right? The theorem was what? If partial p, partial y equals to partial q, partial x on simply connected U, which is of course a subset of R2, then then p dx plus q dy is what? Is exact. All right. Now the reason I called that condition right there the closed condition is simply as follows. Why did I call that the closed condition? The reason I called this the closed condition is simply this. If I take the exterior derivative of p dx plus q dy, what do I get? I get dp wedge dx plus dq wedge dy. How does that simplify? So I've got, partial p, partial x dx plus partial p, partial y dy, wedge dx. Aw, sadness. Oh well. Plus partial q, partial x dx, plus partial q, partial y. These are the total differentials in 2 dimensions, right? And what happens? 2 of those terms vanish because dx wedge dx is 0, and dy wedge dy is 0. What are we left with? We're left with partial p, partial x, minus partial q, partial y, dx wedge dy. And so you see the condition that the form p dx plus q dy be closed is the closed condition. That's why it's a good label for that. It doesn't usually have a label in differential equations. It's just called, that condition for exactness in that particular page in your book, which you reference if you're a typical differential equations class with not much understanding. You just use it, right? All right, so yeah. But my point to you is this is part of a much larger story, and you can actually find generalized potential energy functions for forms of higher degree. And if you study the proof of the Poincaré lemma, you can actually derive those formulas from very specific integrations that arise in the proof of the Poincaré lemma. I actually carry this out for the magnetic field, I think, in my advanced calculus notes. The magnetic field's naturally identified as a 2 form, so the potential energy for a magnetic field would be something like a 1 form in this viewpoint. But the larger point, which is interesting here, is that this Poincaré lemma says that there's a topological condition to say whether or not there's a potential energy function. So that means that there's a connection between physics and topology that's been understood since about 1900. That's when this stuff was found. 1890, 1910, somewhere in there. Now I could give you the best, so I'll stop talking about this in just a second. But, well, I wanted to say one other thing. 2 other things. So an example of a form, if we look at the one form omega equals to minus x dy plus y dx over x squared plus y squared, right? This form, what's its domain? It's R2 with what removed? Right? I mean, it's missing the origin because we got division by 0 there, right? So the domain of this is the so-called punctured plane. I mentioned to you that that's not simply connected, all right? And so what's the problem here? So suppose that omega was equal to the differential of some other thing, beta, all right? Then what would happen if you integrate omega around the unit circle? It would be the integral of d beta around the unit circle, right? And what's the integral of d beta around the unit circle? I mean, you can take P1 and P2 to be equal, right? So this would be like beta of P1 minus beta of P2, which would be, well, that would be 0, right? Because if we integrate a total derivative all the way around, I mean, so omega is a 1 form, so this d beta, let me make this a little less mysterious. Let's call beta f, because it would be a function, yeah? It would be a function. 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 Probably 2 minus 1 would be better. That's usually what I do. All right. Right? So apparently the integral around the unit circle must be 0 if omega is exact. But what is the integral around the unit circle of this form? We can calculate it directly, right? But the integral of omega over the unit circle, how do we calculate that? That's the integral of minus x dy plus y dx over x squared plus y squared, right? I'm going to call this thing c. I'm tired of writing unit circle. So how do you actually do that? How about integral from 0 to 2 pi? What's the parameterization of the unit circle? X equals 2 cosine t, y equals 2 sine t. So what's dx? Minus sine t dt. What's dy? Cosine t dt. What's x squared plus y squared? It's 1. So what do I got? Minus x dy is what? Minus cosine squared dt, right? And then y dx is minus sine squared dt. So what do we got here? We have nothing more than the integral minus the integral from 0 to 2 pi of dt. Oh, no. Well, that is definitely not 0. That's minus 2 pi. What? What's that mean? That means that the assumption that went into supposing that there exists an f on the punctured plane such that omega is equal to df on the punctured plane is false. We have a contradiction. No such f exists. However, funny thing is, you can produce a function such that omega is equal to df on almost the whole plane, but you have to allow for one thing to be left out. There has to be a slit in the plane where you've got this angle jump. Because in fact, what omega is, you want me to tell you what omega is? Here, let me confess what omega is. Omega is the differential of the angle function. And that's why we're getting into trouble. Because you can't define angle continuously all the way around. There has to be a jump, a discontinuity. And if there's a discontinuity, there's also a failure to be able to do differential calculus. And the underlying reason for this is simply that the punctured plane has a topological defect. It's missing a point, which means you can't contract loops to a point there. So anyway, I think that's an interesting example and an important one. All right, so enough about that. I dove kind of deep into that for you guys this semester, partly for math majors in here, partly just because I think it's good for you guys to know about some of these things for your general math education. Let me think about another, here's a calculation we could do born of this. How about let's think about surfaces for a second. If you had a surface, right, how could you describe that? That'd be f of x, y, z equal to what? Some constant, right? So if you had a differential form which was coming from differentiating the level equation for a surface, what should it look like? Something like partial f partial x dx plus partial f partial y dy, right, plus partial f partial z dz equal to 0, right? But let's see here. I guess you could ask the question, I mean, that's df is my larger point. So you might ask the question is like m dx plus n dy plus, I don't know, r dz. If we look at that equal to 0, could we understand that as being, as the solution set being, you know, some sort of surface, right? So it would make sense to ask the question, is that an exact equation? In the sense, can I rewrite this? Can I rewrite this, right, as df equals to 0, and then say, aha, the underlying surface is really just f of x, y, z equal to 0, right? What condition would you need on m, n, and r in order that this would be the case? Well, I think if m, n, and r are really, as they're advertised, if they're df, then you should be able to say that d squared, that d of df is 0. Well, if you look at d of df being 0, that gives you 3 closed conditions on m, n, and r, which are equivalent to saying that the curl of m, n, r is 0. My point to you is that this is just a larger family of analysis, and there's a deeper calculus to discover here, ultimately culminating in something called the Frobenius theorem, which has almost nothing to do with the Frobenius theorem that you will be happy I'm skipping this semester. So, Frobenius was this rather formidable late 19th century mathematician who did deep work in a lot of different things. So, as a math major, you might run into his theorems in different courses and wonder if it's the same Frobenius. The answer is yes, as far as I know. Do you know anybody last name Frobenius? I don't remember ever having a student with the last name Frobenius. I've seen a lot of different names, but never Frobenius. I'd remember that. No? I'm sorry. I forget you guys are still worn out from the game, like the excitement of it all. Still coming down from the high, which is winning in football. Am I right? No? All right. Okay. All right. Well, with that, I will get back to the usual fare. Usual stuff. So, next order of business, let's talk about the integrating factor method. This is a hard segue. I guess I'll start it over here. Oh, by the way, this actually, I will fess up. This in part was an advertisement for advanced calculus where I actually derive things. Like in a typical advanced calculus course, I'll actually work out the Poincare lemma and things like this. About half of my advanced calculus is thinking and trying to understand differential forms more deeply. So, and also, hopefully, doing some like tensor calculations. These are the sort of math that you can run into in, you know, higher level engineering that some of you might see in grad school, because some of you are going to engineering grad school. There is a contingent of you who are thinking about doing that. You exist here somewhere, possibly in this class. I believe in it. Who here is planning to go to engineering grad school? No! Oh, man. Dang it. Why did I? Oh, nuclear chemistry. Okay, nuclear chemistry. Relevant. Thank you. All right. You saved my lecture. Otherwise, I was just talking to myself for the last hour, you know? But at least I get paid, right? So there's that. But I hope you guys found something I did interesting. I don't know. You can debate. All right, integrating factor method. So we wish to solve. Here's what we wish to solve. dy dx plus py equals to q. This is, we wish to solve. Explicitly. Now here, P and Q are functions of x alone. All right? Show of hands, who remembers how to do this from Calculus 2? I have one intermediate show of hand. Actually, just a finger. I think it has. I judge your confidence about this at 70%. 50? Okay. Very good. So I'll do what I always do here, and I think this is productive. I'm going to work out the general result, and I'm going to do an example at the same time. So what's going to be going on here is general problem, how we solve it, how that's applied to a specific case. All right? And the reason for this is to drive home a point, which is that the method of proof for this method is actually the method of calculation for this method. They're one and the same. So here it is. First of all, step one, put into standard form, which means we've got that dy dx. Well, let me just call this is star. That's the standard form right there. All right. So I guess to make things interesting over here, I'll start us out with something that's not in standard form. Like, I don't know, x dy dx plus y equals to x. There. Oh no, it's not in standard form. However will we fix it? Divide by x. Okay, so dividing by x, we get dy dx equal plus 1 over x times y is equal to 1. There we go. Now we have put my problem into standard form. That's the first order of business. And identify, here's also part of the, let me add a little bit here, identify p and q. So what's p equal to here? P is 1 over x, right? What's q? Q is 1, right? So there you go. Actually, all that really matters is that we identify p. Identifying q is not really needed, but just, okay. Step number 2. Let I equal to the exponential of the integral of p dx. All right, so step number 2, we set I, which is the integrating factor, equal to the integral of dx over x for us, this case. All right. And so that's the, what is that? That is natural log of the absolute value of x. Oh, man. What did I forget? So embarrassing. I tell you. What am I missing? This is non-negotiable. It's got to be there. Exponential. So exponential of the integral of dx over x. So we've got exponential of the natural log of the absolute value of x, which is just the absolute value of x. So when you get the absolute value of x as your integrating factor, that, if you think about that, that means that this is equal to plus or minus x, depending on whether x is positive or negative. So as you understand this technique more deeply, you realize that it suffices to just multiply by x in the next step. So step 3 is to multiply the equation in standard form by I. So what we're going to have is I dy dx plus IP y equals to IQ. Right? So for this one, so by the way, there's some kind of thinking here, but you know, I equals x does just fine. There's no harm in dropping the absolute value. We'll see that.